Right. What we're going to recap now is rates of change, because all of the next few things that we're going to do all involve rates of change. Okay? So just a reminder of what we saw last year, with our rates of change questions, it might involve more than one rate in order to solve the problem, and we might have to link a few together. So let's, using this basic idea, implicit differentiation is another way I suppose we could call that, because it was the same idea, you'll remember. If we want to differentiate in terms of t, but we can't do it in terms of t, we'll do it in terms of x and multiply by dx of t. So that was also using this idea. The chain rule uses this same idea. Okay? But it's also the basic idea for rates of change. So let's imagine a bit of thought exercise here. You've got a spherical balloon. So you've all got a balloon, okay? And it's being deflated so that the radius of the balloon is decreasing at a constant rate. There's mine going down. Can you see? Is yours going down? There we go. At 10 millimeters per second. Calculate the rate of change of volume when the radius of the balloon is 100 millimeters. Because you see, even though the radius is going down at a constant amount, the air, or the volume of air, is not. That's why if you think of your balloon, think of the noise it's making. See, it goes real quick later, doesn't it? It goes. So it's not constant. Let us prove that. dv to t is what we want to find. We've been told dr to t, change of radius, and it's negative because it's decreasing. So we know dr to t, we want dv to t. If there's some way of linking volume and radius together, then we can find dv dr, and we've got a formula. Well, we do have a formula for volume. It is, of course, 4/3 pi r cubed. The derivative that always fascinates me, dv dr, turns out to be 4 pi r squared, which is, of course, yes. So the rate of change of the volume at any point in time is equal to its surface area. I always find that amazing. Anyway, let's sub in. So we've got minus 10 times 4 pi r squared, so minus 40 pi r squared. So we can see it's not constant. It's determining on the radius. So the bigger the radius, the larger the volume that's being expelled from our balloon. We want at the time when the balloon is 100 millimeters. So let's substitute that in, and we get minus 400,000 pi. So there we go. It's decreasing at 400,000 pi millimeters cubed per second. Okay, now we're blowing a bubble. Okay, go to there's your soap bubble. So this time the volume is at a constant rate. We're blowing into our bubble at a constant rate. But the surface area, that won't increase at a constant rate. That, of course, will change as we're blowing it in. So we want to know the increase in surface area. So I've called it S for surface area. ds to t is what I want to find this time. Now, we've been told dv to t is 70. Now, if I can link dv and s, a bit hard to link velocity and surface area together, other than that one we just saw. So, what I can do is I can link velocity with radius. I can also link surface area with radius. So, using 3 derivatives, I'll be able to come up with an answer here. So, there's our dv dr that we just found. Let's now find ds dr, so differentiate surface area. And that's everything now. We can sub into our formula, and we end up with 140 over r. So the rate of change of the surface area is inversely proportional to the radius. So the bigger the radius, the slower the surface area is increasing. Think about blowing up a balloon. That makes sense. You know, when you start off, it goes really quickly, but then as you blow more and more in, it seems to just go up a little bit, and then as it's getting really big, everyone's holding their heads because they think it's going to burst. Oh no, don't do another breath. And it goes up a little bit. Wish I had a balloon. We could simulate that, couldn't we? Okay, so sub in when r equals 10, dv to t, and there it is. So it was 10 millimeters. At that point in time, the surface area is increasing at a rate of 14 millimeters squared per second. So, okay, just look, we did look at this last year a little bit, so I've just grabbed a handful of questions out of each of those exercises to have a bit of a recap on rates of change.